All right, now that we've established what terms go into our one-dimensional motion, we want to derive the kinematic equations that help describe motion in a straight line. And so we're going to have to derive these equations from things that we already know or other logical situations. And so this is the derivation of one-dimensional kinematic equations. Okay, and I think what we'll do for simplicity's sake is we're going to derive them in the x direction. Now this will work just as easily in the y, the z, but we're going to just do them in the horizontal, or what's traditionally called the x direction, for simplicity. Then I don't have to worry too much about vectors and these sorts of directional things. And the other condition that we are going to set is, again, one that we established last time, and that is one of constant acceleration. So this is derivation of one-dimensional kinematic equations, and we'll just write that we have constant acceleration and we're doing this in the x direction. And so let's start with a definition that we already have, and in fact one that we just finished coming up with, and that is the acceleration definition itself. And so if we scroll back up to our equation, not this one, but the average acceleration equation that we had, if it's okay with everyone, I'm going to call that equation A. I'm going to grab that and bring it down here and write it in terms of the x direction. So we'll just write in the x direction, the average acceleration is equal to the initial velocity, or so I should say the final velocity in the x minus the initial, all divided by the change in time. And so what we're looking at there is just something that tells us that in the x direction, the average acceleration is equal to the difference between the two velocities, again, in the x direction, that's what that sub x2 and x1 are for, divided by the time. We can simplify this very easily by thinking about when we are starting this problem. When we do these kinematic problems, we don't know the exact date and time. It's not like we're subtracting T2, which is like September 21st, 2021, minus, at 9:30 a.m. minus some other time. When we talk about a time interval, what we really are talking about is usually starting our problem at t equals 0. And so if you start your problem at t equals 0, well then your delta t and your t2 are the same thing. And so basically what I think we should do to simplify our problem, and so the best way that we can handle that is to actually set our t1 equal to 0. So we'll start measuring from that time. And that means that t2 is the same thing as delta t. And we can leave it as delta t if we want, but oftentimes it is just written as t. You'll see it sometimes as delta t, sometimes written as t. And that t is the time interval itself. And so now our equation A, and of course we don't have to even have the average because we know that all averages, that all accelerations here are average. So if it's okay with everyone, I will set the average acceleration here to just call it acceleration, since acceleration is constant. All right, and so don't want to go too far because we're basically taking that equation up there and we're going to rewrite it in a much more neat form of ax is equal to vx2 minus vx1, all divided by just t. And what we'll do is we will simplify this equation, rearrange it in terms of vx2. Remember what vx2 is? It's the final velocity, which is often something that we're looking for. Oftentimes we're given initial conditions and we're asked to find what the final velocity is. And so we'll do a little cross multiplying here. We'll get the t up there to begin with, and that makes the equation axt is equal to vx2 minus vx1. And finally, we'll rearrange for vx2, or the final velocity equals the initial velocity plus the acceleration times time. And that is our very first equation. And that equation is saying that if you're looking for the final time, or really any unknown in that equation, as long as you have the other three, you can find the fourth one. And the four values in there are the final velocity, the initial velocity, the acceleration, and the time. So the only thing that we don't have any information for is displacement. It's just a relationship between velocity, acceleration, and time. Now, if we wanted to rewrite this in terms of our vector form, it would look like this. Now, we will be using it originally in the one dimension, usually x to begin with, and then y. And so we will use it in that x form, but I want to put that there. These are the same equation. This is just in the x direction. All right, great. And of course, on this side, you see the vector signs here are taking care of the direction part of the vector, while over there the x is playing the same purpose. All right, so that's the easy one. What can we do to get ourselves some more equations? Well, let's take the equation for the average velocity that we had before. So instead of starting with acceleration this time, let's start with our average velocity equation. And you'll remember from previously we had derived it. I'll just go back up and see what it was. There we go, right there. And I'll put a little b there as well. No, I don't want to misunderstand it. So this is our b equation. And so our b equation here is that the average velocity is just equal to our change in position divided by our change in time. We can rewrite that here as the average velocity in the x direction is equal to our change in position. In the x direction, that's just x2 minus x1. And we're dividing that by our time interval, so either delta t or just t is fine. Okay, so that looks pretty interesting, except average velocity is not that interesting to me. It's your instantaneous velocity, that is v2 and v1, the velocity at particular positions, that is much more important. But this is going to prove to be an important step in getting us to where we want to go with the equations. We just need one more equation to combine with this one to create our next kinematic equation. The next equation that we're going to use is one that is not really a physics equation, but more of a mathematical equation. And that's the equation of averages themselves. If this is the equation for the average velocity, well, in general, we know what average velocity is if acceleration is constant. And so we can write the average velocity another way. If you're not sure what I'm talking about, think about what the average of any two numbers is. If I had any two numbers, of course I would just add them up and divide by 2. Well, it turns out I can do the same thing with my velocities. If I take my final velocity and I add it to my initial velocity, I divide by 2, that gives me my average velocity, the way we've set these problems up. And so now what we have is interesting because we have two equations that both describe the average velocity of an object. And even though I don't really care about the average velocity of that object, I do care that those two values are equal to each other, or those two equations are equal to each other. So let's make the right-hand side of those two equals and see what happens. And so just for our notes where this came from, let's make it an arrow. So this is definition of the average of two numbers. All right, so let's take the left hand or the top equation, make that the left hand side. X2 minus x1 divided by t is equal to, what do we have here? Vx2 plus Vx1, all divided by 2. And I think in this case, what we'll try to do is to solve for final position. And so let's see if we can rearrange this fairly complicated looking equation to solve for final position. Let's cross multiply by t to begin with. So we'll take the t from the left hand side, bring it up to there. And so the left hand side just becomes x2 minus x1. The right hand side is now Vx2 plus Vx1, all divided by 2, all multiplied by t. All right, so far so good, but we're going to need a little bit of a substitution to simplify this into the form that we want. And the way we're going to do that is to use our equation number 1. We've already derived the equation that the final velocity is equal to the initial velocity plus acceleration times time. And so what I'm going to do is I'm going to take this equation, Vx2, I'm going to plug it into there. And what that allows me to have is it takes out my Vx2 and gives me acceleration, which wasn't there originally. So that's something that's desirable in this case. So let's go ahead and do that. So using 1, sub in Vx2. And so now my equation becomes x2 minus x1 is equal to, well, instead of Vx2, I have Vx1 plus axt. I want to make sure that x is a sub x. And another Vx1. That Vx1 was from here. And finally, all divided by 2, all multiplied by t. So I've gone from there to there by just substituting in my Vx2 term. Nothing too tough, but I can quickly see that there's going to be some simplifications that can happen with this equation, so let's make them. Of course, we see that we have 2 Vx1, so we're going to add them up, but after we add them up, let's also divide by 2 and multiply by t, and then the other term here, this axt term, we're also going to multiply by t and divide by 2. So basically we're expanding the brackets now to get it as we like. And so we'll simplify this to 2Vx1 plus axt, all divided by 2, multiplied by t. And one more time, expanding the bracket, 2 divided by 2 is just 1. And then we have Vx1 times t. The rest of it sticks together. We have our 1/2 term going with this value here. And we have axt, and we have a t and another t, giving us t squared. And finally, we can write our left-hand side again as x2 minus x1. That form of the equation is just fine, though people will most often write it with the x1 term on this side of the equation so that you've already solved your equation for its final value, which is x2. So the final position is equal to the initial position plus the initial velocity multiplied by time plus 1/2 the acceleration times time squared. So quite a bit more, I think, intense than that first equation, also giving us different information. This equation is does have our position information in it, but now it doesn't have final velocity. Notice that Vx2 is not in this equation at all. We got rid of that. And so it's a relationship between position, initial velocity, acceleration, and time only. If we were to write this in its most general form, again, we could write it in terms of r or s. They tend to be our general position terms. It would look like this. There we go. Okay, great. So we're going to go ahead and try to derive one more equation. This one can be quite tough. And that's going to be it. We're only going to need 3 kinematic equations. So our goal will be to solve for let's see, we'll solve for t in equation 1 and sub into 2. So equation 1 and sub into equation 2. And then we will solve for, I think, the final velocity in that one. Okay, so let's grab equation 1. Where did it go? It's just Vx2 equals Vx1 plus Axt. So Vx2 equals Vx1 plus Axt, like so. Again, now we're solving for the time. And so we get that time is equal to Vx2 minus Vx1, and we'll divide both sides by a following that, giving us this equation here. And now we'll take that equation and we'll sub it into equation 2 for every place that we have the time. And so our equation was x2 equals x1 plus Vx1 times t, and so then we multiply it by this term, Vx2 minus Vx1, all divided by Ax. And finally we have our last term, which was our 1/2 times acceleration times t squared this time. And so even further more difficult here, we have Vx2 minus Vx1 all divided by Ax, and this is a squared term. So we were able to eliminate time in this equation, and now we have everything except time. We have our initial velocity, our final velocity, our initial position, our final position, and time, as well as acceleration. Oh, sorry, not time. We have acceleration and not time, and so it's a useful equation as well that we need to clean up a bit, certainly. So let's see what we can do. So just expanding the brackets to begin with. So that takes care of that term, this term here. And so moving on to the final one, we're going to have to bring our Ax squared out here to simplify. And so Ax divided by Ax squared will obviously just be 1 over Ax. We'll deal with that in the next line. But we still have our Vx2 minus Vx1 squared, which I can handle at this time. So I'll just go ahead and write this as Vx2 squared minus 2 Vx2 times Vx1 plus Vx1 squared. There we go. All right, so looking messy, very messy. Let's see if we got any shot of cleaning this up and getting something simple. And finally, I'll do this term last, just because it's the most intimidating, giving me Vx2, Vx1, all divided by ax, and the two t's have canceled out. All right, let's see if there's anything there that we can simplify. And certainly it looks like there's some like terms. And so this one and this one look very natural. In fact, it looks like they cancel one another out completely. And then other than that, we can combine these three together and see what we get. All right, so we still have x2 equals x1. The Vx2 term is canceling with that one. And so now let's logically put this together. We still have our Vx2 squared divided by 2ax. That looks good. And then I have a negative 1 plus a half, giving me a negative half. And so this becomes minus Vx1 squared, all divided by 2ax. Again, looking very, very hairy. Most likely, you won't necessarily be doing this sort of derivation in any kind of quiz or test, but absolutely knowing where it comes from is a useful exercise. And so finally, we can finish this problem off. We'll make this x2 minus x1 on the left-hand side, and we'll take the like term of 1 over 2ax out of these two terms, leaving us with Vx2 squared minus Vx1 squared, multiplying both sides by 2ax, and traditionally we have the velocities on the left-hand side. So if it's okay with everyone, I'll write this as Vx2 squared minus Vx1 squared is equal to 2ax, since I multiplied that through on both sides, multiplied by x2 minus x1, and finally we'll write this in its final form as the final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration multiplied by the change in position. Like so. And that gives us our third kinematic equation. And so we can rewrite that if we wish in its vector form. Like so. We'll find that useful in the future, but for now, we'll stick with the x direction. Now, looking at this equation, we now have 3 kinematic equations, and that's all we're going to need. That's all we're going to need to do all of the kinematic work in one dimension. Now, for those people that have taken physics in the past, you may have had 4 equations, you may have had 5 equations, but in fact, those other equations are redundant. These 3 kinematic equations that we've now derived are the only 3 we're going to need to solve our one-dimensional kinematic problems.